Ladies and gentlemen,
History is not always made with fanfare. Sometimes it arrives quietly, hidden in streams of data, buried inside equations, and overlooked until a single confirmation changes everything. Today we stand at one of those moments. A moment when a distant object, once thought to be just another faint signal in the sky, has forced the scientific world to pause and reconsider what it knows. That object is known as three-eyed ALAS, and the confirmation of its true size has reshaped our understanding of what moves through our cosmic neighborhood. When three-eyed ALAS was first detected, it appeared unremarkable, small, dim, and easily lost among countless other celestial bodies. Initial estimates placed it within familiar boundaries, something that could be explained using existing models and past observations. But science is not built on assumptions. It is built on verification. As observations continued and instruments gathered more precise data, inconsistencies began to appear. Measurements did not align. Brightness varied in ways that defied expectations. Trajectory models hinted that something about this object was being underestimated. Then came the confirmation. After deeper analysis using multiple observation methods, the true scale of three-eyed ALAS emerged, and it was far larger than anyone had anticipated. This was not a minor adjustment or a small margin of error. It was a fundamental correction. The size of three-eyed ALAS placed it in a category rarely seen before, immediately elevating it from curiosity to historical significance. Such objects are not supposed to be this large, this intact, and this measurable at this stage of observation. This revelation sent shockwaves through the scientific community. Models that once seemed reliable now required revision. Long-held assumptions about how objects form, survive, and travel through space were suddenly open to question. If three-eyed ALAS could exist at this scale, what else might be moving through the dark, unseen corridors of our solar system? How many similar bodies have passed undetected simply because expectations limited what researchers were looking for? What makes this discovery even more remarkable is what it suggests about cosmic survival. An object of this size must have endured violent forces, stellar radiation, gravitational disruption, and vast stretches of time. Its existence implies resilience on a scale that challenges our understanding of material strength and structural cohesion in space. It is a reminder that the universe often preserves what we assume should not last. Beyond the scientific implications, this moment represents something deeper. It demonstrates the power of patience, precision, and humility in exploration. The universe does not reveal its secrets easily. It requires repeated observation, willingness to be wrong, and the courage to accept results that disrupt comfort and familiarity. Three-eyed ALAS did not change history because it appeared, it changed history because its truth was confirmed. As this object continues its journey, it will be studied, debated, and referenced for decades to come. Textbooks will be updated. Simulations will be rewritten. Future discoveries will be compared against it as a new benchmark. But perhaps its greatest contribution is the reminder it gives us that discovery is not finished, and certainty is always temporary. Tonight, as we look up at the sky, we are reminded that even now, the universe is capable of surprising us. Something vast crossed our awareness, not with drama, but with data, and in doing so, it expanded the boundaries of what we thought was possible. Three-eyed ALAS has made history, not because it sought attention, but because it revealed a truth we were not prepared to see. When three-eyed ALAS was first detected, it did not announce itself as a breakthrough or demand special attention. It appeared in the data the same way countless other faint objects do, an unassuming point of light against a crowded and constantly shifting sky. Automated surveys record thousands of such signals every night, most of which turn out to be routine asteroids, distant comets, or transient noise that fades with further observation. In this context, three-eyed ALAS blended in perfectly, offering no immediate reason to believe it would become anything more than another catalog entry. The initial observations suggested a small, dim object with characteristics well within expected ranges. Its brightness was low, its motion appeared predictable, and its signal strength did not trigger any alerts beyond standard follow-up procedures. Based on early photometric data, its estimated size placed it comfortably among objects already well understood by astronomers. There was nothing in its early profile that challenged existing theories or hinted at an anomaly. In fact, if not for routine tracking protocols, it might have been logged and forgotten entirely. This kind of beginning is common in astronomy. The vast majority of discoveries do not arrive with dramatic revelations. They start quietly with incomplete data and cautious assumptions. Observational limits play a significant role at this stage. Distance, viewing angle, background light, and instrument sensitivity all affect how an object first appears. A faint object can seem small simply because it reflects little light or because its surface properties are unknown. Early size estimates are often provisional, shaped more by probability than certainty. At the time of its discovery, 3 fit neatly into these expectations. Its faintness suggested modest dimensions, and its behavior showed no immediate irregularities. There were no sudden changes in brightness, no unexpected acceleration, and no visible structure that stood out from similar detections. In a sky filled with millions of objects, it was statistically easier to assume familiarity than to suspect rarity. This initial underestimation reflects how scientific classification works in practice. Early labels are not final judgments, they are placeholders based on limited evidence. Astronomers prioritize efficiency, especially in wide field surveys designed to scan massive portions of the sky quickly. Only objects that break obvious rules receive immediate scrutiny. Everything else waits its turn. 3ITS at first glance obeyed the rules, yet this ordinary beginning is precisely what makes the later revelation so significant. The fact that such a historically important object could pass unnoticed in its earliest phase exposes the subtle challenges of cosmic observation. The universe does not highlight its most extraordinary features. It presents them quietly, wrapped in normality, requiring patience and repeated measurement to uncover their true nature. The early dismissal of 3 was not a failure of science, but a demonstration of its caution. Scientists resist dramatic claims without sufficient evidence. They trust the data they have, while remaining open to revision. In this case, the data initially pointed toward normality. Only with time, additional observations, and improved analysis did that assumption begin to erode. In retrospect, the unremarkable first impression of 3 serves as a reminder that discovery is a process, not a moment. Extraordinary truths often begin disguised as ordinary facts. The universe does not reveal its scale all at once. It waits, quietly, until curiosity and persistence uncover what was hidden in plain sight. Early measurements of 3 relied on limited observational data, and those constraints played a decisive role in underestimating its true size. When a distant object is first detected, astronomers must work with brief snapshots rather than long-term records. Initial brightness readings, motion tracking, and reflectivity estimates are often incomplete, gathered under imperfect viewing conditions and processed quickly to determine whether the object warrants continued attention. In the case of 3 these early data points painted a picture that seemed familiar and comfortably within expected parameters. One of the main reasons for this underestimation lies in how size is inferred rather than directly measured. Astronomers typically estimate an object's dimensions based on how much sunlight it reflects, an approach that depends heavily on assumptions about surface composition and albedo. A dark, low reflectivity surface can make a large object appear deceptively small, while a highly reflective surface can exaggerate the apparent size of a much smaller body. With no immediate indication that 3 had unusual surface properties, standard assumptions were applied, naturally skewing the size estimate downward. Distance also played a critical role. At the time of its detection, 3 was far enough away that small uncertainties in distance measurement translated into large uncertainties in size. A minor error in estimating how far away the object was could significantly alter calculations of its brightness and scale. Early trajectory models, built from a short observational arc, lacked the precision needed to correct for this. As a result, the object's apparent faintness was interpreted as evidence of small physical dimensions rather than a consequence of observational geometry. Instrumental limitations further compounded the issue. Survey telescopes are optimized for wide coverage rather than detailed characterization. Their strength lies in finding objects, not in fully defining them at first glance. Resolution limits, atmospheric interference, and background noise all affect how much detail can be extracted from a single detection. For 3 these limitations mask subtle clues that might have hinted at its true scale, reinforcing the assumption that it was an ordinary, smaller body. Another contributing factor was statistical expectation. Most newly discovered objects fall within a predictable size range, and scientific workflows are designed around that probability. When data is ambiguous, it is often interpreted in favor of the most common explanation. In this case, that meant treating 3 as one of many small objects rather than an outlier. This is not bias in a negative sense, but a practical necessity when processing vast amounts of observational data every night. Over time, as additional observations were gathered, cracks began to appear in the original estimates. Slight variations in brightness, inconsistencies in reflectivity, and subtle changes in motion hinted that something was off. These discrepancies did not immediately reveal the object's true size, but they signaled that the early assumptions might be flawed. Each new data point added tension between expectation and reality. The underestimation of 3I Vatilas's size ultimately illustrates a fundamental truth about astronomical discovery. Early measurements are provisional by nature. They are shaped by limited data, necessary assumptions, and the constraints of available technology. Only through repeated observation and refinement can those early impressions be corrected. What began as a reasonable estimate based on incomplete information eventually gave way to a far more astonishing reality, proving that the universe often hides its greatest surprises behind the veil of initial uncertainty. As observations of 3I Vatilas continued, subtle inconsistencies began to emerge that challenged the simplicity of the initial assessment. These were not dramatic anomalies that immediately demanded attention, but small deviations that accumulated slowly, only becoming meaningful when viewed together over time. In astronomy, such details matter deeply. When an object behaves just slightly differently than expected, it can indicate that underlying assumptions are incomplete or incorrect. In the case of 3I Vatilas, these early warning signs appeared in its brightness patterns and its motion through space. One of the first irregularities involved changes in brightness that did not fully align with standard models. As the object was tracked across different observation periods, its reflected light varied more than anticipated. Normally, such variations can be explained by rotation, shape, or changes in viewing angle. However, when these factors were accounted for, the fluctuations remained larger than expected for an object believed to be relatively small. The light curve suggested either an unusually complex surface or a much larger body than initial estimates implied. Motion provided another clue. Early trajectory calculations assumed a predictable path consistent with similar objects, but as more positional data was added, slight discrepancies began to appear. These deviations were subtle, small enough to fall within acceptable margins at first, but persistent enough to raise questions. When an object's observed position repeatedly drifts from predicted models, it often indicates that the initial parameters, such as mass or size, may be incorrect. For 3I Vatilas, the mismatch between predicted and observed motion hinted that its gravitational behavior was not being fully captured. The combination of brightness anomalies and trajectory irregularities created a growing sense of uncertainty. Individually, each inconsistency could have been dismissed as noise or measurement error. Together, they formed a pattern that could not be easily ignored. This is how scientific doubt takes shape, not as a single moment of realization, but as a gradual erosion of confidence in the prevailing explanation. With each new observation, the idea that 3I Vatilas was an ordinary, small object became harder to defend. These inconsistencies also highlighted the limitations of early observational windows. Short observation arcs can produce deceptively clean models that later fall apart as more data is introduced. As tracking extended over longer periods and different viewing geometries, hidden complexities became visible. The object's behavior refused to settle neatly into established categories, suggesting that the framework used to interpret it needed revision. As doubts grew, the object began to attract closer scrutiny. Researchers revisited earlier data, reprocessed measurements, and tested alternative models. Could the surface be darker than assumed? Could the object be elongated or irregular in shape? Or was the simplest explanation also the most disruptive, that 3I Vatilas was far larger than originally believed? Each possibility was weighed carefully, guided by evidence rather than speculation. What made this phase especially important was its role as a turning point. Inconsistencies serve as the engine of scientific progress. They are the signals that something new may be hiding beneath familiar appearances. In the case of 3I Vatilas, the growing mismatch between expectation and observation transformed routine tracking into focused investigation. The object had not changed, but understanding of it had. Those early doubts marked the moment when 3I Vatilas began its transition from an overlooked detection to a subject of serious scientific attention, setting the stage for the revelations that would follow. As questions surrounding 3I Vatilas intensified, researchers shifted from routine monitoring to a far more comprehensive investigative approach. No single observation or instrument could resolve the growing uncertainties, so the object was subjected to a layered process of verification that drew upon multiple observation techniques. This shift marked a critical stage in the discovery, where confirmation became the priority and assumptions were systematically tested against independent data sources. One of the first steps in this advanced analysis involved extending the observation timeline. By tracking 3I Vatilas over longer periods, scientists were able to refine its trajectory with greater precision. Longer observation arcs reduce uncertainty in orbital calculations, allowing even minor deviations to be identified and corrected. With each additional data point, predictions became more accurate and earlier simplifications began to break down. This alone provided valuable insight, as improved trajectory models started to reveal inconsistencies that could no longer be attributed to measurement noise. In parallel, observations were gathered using different types of instruments. Wide-field survey telescopes, which excel at detection, were supplemented with more specialized systems capable of higher resolution measurements. These instruments offered improved sensitivity to brightness variations and finer positional accuracy. Observing the same object through different technological lenses allowed researchers to cross-check results, ensuring that no single instrument's limitations were skewing the conclusions. Spectral analysis also played an important role in this reassessment. By examining how 3i loss reflected and absorbed light across different wavelengths, scientists could infer details about its surface properties. This information was crucial for refining size estimates, as it helped determine whether the object was unusually dark or reflective. Adjusting these parameters in the models led to significant changes in calculated dimensions, gradually pushing estimates beyond the ranges initially considered plausible. Another key element was the use of independent modeling teams. Separate groups analyzed the data using different assumptions and computational methods, reducing the risk of shared bias. When multiple models developed independently began to converge on similar results, confidence in those results increased. This convergence was especially striking in the case of size estimates, where revised calculations repeatedly pointed toward a much larger object than originally thought. Gravitational modeling further strengthened the analysis. As the object's path was recalculated with higher precision, its interaction with surrounding gravitational influences was examined more closely. Even slight deviations in motion can reveal information about an object's mass and structure. Incorporating these effects into simulations produced trajectories that aligned more closely with observed positions, but only when larger size parameters were used. This phase of investigation was not driven by a desire for sensational outcomes, but by methodological rigor. Each step was designed to eliminate uncertainty rather than create it. Data was revisited, assumptions were challenged, and alternative explanations were tested exhaustively. The goal was not to prove that 3i was extraordinary, but to determine what explanation best fit the evidence. Through this multi-layered approach, a clearer picture began to emerge. What once seemed like minor anomalies were now supported by robust, cross-verified data. The use of multiple observation techniques transformed suspicion into substantiated understanding, laying the groundwork for the confirmation that would soon follow. When the revised calculations were finally completed, the results were impossible to ignore. The confirmed size of 3i was not just slightly larger than early estimates, it was dramatically beyond them. What had once been categorized as a modest, unremarkable object now occupied a scale that demanded reclassification. This was the moment when uncertainty gave way to clarity, and the implications of the discovery became unmistakable. The updated measurements emerged from the convergence of multiple analytical methods. Independent size estimates, derived from refined brightness models, spectral data, and improved distance calculations all pointed toward the same conclusion. Each method, when applied separately, suggested a significantly larger object. When combined, they reinforced one another with striking consistency. This alignment across techniques removed much of the ambiguity that had plagued earlier assessments and replaced it with a level of confidence rarely achieved in the early stages of discovery. The magnitude of the correction itself was what stunned researchers. Scientific revisions are common, but they are usually incremental. In this case, the difference between the original estimate and the confirmed size was large enough to alter how the object fit into existing categories. It was no longer comparable to the majority of objects detected by similar surveys. Instead, it stood out as an extreme example, one that occupied the upper limits of what models had predicted could exist and remain intact. This dramatic shift forced scientists to confront the consequences of their assumptions. Earlier models had relied on typical values for reflectivity, density, and shape. With those assumptions revised, the object's true dimensions expanded rapidly. What initially appeared faint was now understood to be the result of distance and surface characteristics rather than small physical size. The realization reframed earlier observations, revealing that the clues had been present all along, hidden behind incomplete interpretation. The confirmation of such an unexpected scale carried immediate theoretical implications. Objects of this size are rare, and their existence challenges ideas about formation and survival. How could something so large persist without being fragmented by gravitational interactions or eroded by radiation over immense spans of time? The confirmed size of 3I at last demanded answers to these questions, pushing researchers to explore scenarios that had previously seemed unlikely or unnecessary. Beyond theory, the confirmation altered practical priorities. An object of this scale warranted sustained monitoring and detailed study. Observation schedules were adjusted, and future tracking became a higher priority. The discovery was no longer just about correcting a measurement, it was about recognizing the significance of what had been found. The object's size alone made it a valuable source of information about the dynamics of the solar system and the broader environment beyond it. What made this moment particularly powerful was the certainty that accompanied it. Doubt had been gradually replaced by evidence, and speculation by verification. The size of 3I Atlas was no longer an estimate built on fragile assumptions, but a conclusion supported by robust, cross-validated data. This transition marked a turning point, transforming a once-overlooked detection into a landmark discovery and setting the stage for the profound questions that would follow. Once the true size of 3I Atlas was confirmed, its classification could no longer remain unchanged. The object no longer fit comfortably within the familiar categories used to organize most celestial discoveries. Instead, its dimensions placed it into a rare and largely unexplored class, one that exists at the margins of current astronomical understanding. This shift in classification was not merely a matter of labels, it represented a fundamental change in how the object was perceived and studied. Most objects detected by modern surveys fall into well-defined size ranges, allowing them to be grouped with relative ease. These categories help scientists predict behavior, origin, and long-term evolution. However, 3I Atlas exceeded those expectations. Its scale pushed it beyond the upper boundaries typically associated with similar detections, immediately marking it as an outlier. Outliers are invaluable in science because they expose the limits of existing frameworks and point toward gaps in knowledge. Placing 3I Atlas into this rare category carried significant implications. Objects of such size are uncommon not just because they are difficult to detect, but because their very existence raises questions about how they form and survive. Conventional models suggest that bodies of this scale should either fragment during formation or be altered dramatically by gravitational encounters over time. Yet 3I Atlas appeared intact, coherent and dynamically stable, contradicting those expectations. This unusual status prompted comparisons, with only a handful of known objects that share similar characteristics. Each comparison revealed important differences, reinforcing the idea that 3I Atlas was not simply a larger version of something already understood. Instead, it represented a distinct case, potentially shaped by conditions or processes that are not well represented in current data. The rarity of such objects meant that even small details carried disproportionate importance, as they could inform entirely new lines of inquiry. The reclassification also influenced how scientists approached observation strategy. Objects in this category are treated as high-value targets because they can yield insights unavailable from more common discoveries. Extended observation campaigns, higher resolution instruments, and more sophisticated modeling efforts were justified by the object's exceptional nature. The scientific community recognized that opportunities to study such a large and unusual object are infrequent, making comprehensive analysis essential. This new category status also had broader implications for population estimates. If one object of this size could be detected, it suggested that others might exist, either undiscovered or misclassified due to similar observational challenges. This possibility encouraged a reevaluation of survey data and detection thresholds, raising the question of how many rare objects might be hidden among seemingly ordinary detections. The existence of 3I Atlas hinted that the distribution of object sizes could be more complex than previously assumed. By occupying this unprecedented category, 3I Atlas became more than a singular discovery, it became a reference point. Future detections would be measured against it, and theoretical models would need to account for its characteristics. Its classification marked the transition from anomaly to benchmark, redefining expectations and expanding the boundaries of what is considered possible in our cosmic environment. The placement of 3I Atlas into such a rare category immediately exposed weaknesses in existing astronomical models. These models, built over decades of observation and refinement, are designed to explain how objects form, evolve, and behave within well-established physical limits. They work remarkably well for the vast majority of known bodies. However, the confirmed scale of 3I Atlas pushed those models into uncomfortable territory, where predictions became uncertain and explanations incomplete. At the heart of the issue was formation. Standard models describe how objects gradually grow from smaller fragments through accretion, collisions, and gravitational clustering. As size increases, So do the forces acting on the object, making stability increasingly difficult to maintain? Beyond certain thresholds, models predict fragmentation, deformation, or dramatic alteration. The sheer size of 3I v80 loss challenge these thresholds. According to prevailing theories, an object of this scale should not easily form without leaving clear signatures of disruption. Yet observations suggested a coherent and enduring structure. Survival posed an equally serious problem. Large objects are subject to intense gravitational interactions as they move through space. Close encounters with planets, stars, or dense regions can tear them apart or dramatically alter their trajectories. Over long periods, radiation and thermal stress further erode their structure. Existing models assume that objects of exceptional size are unlikely to remain intact for extended durations. The continued stability of 3IA Attilas therefore forced scientists to question whether these destructive processes are fully understood or whether certain materials and configurations are more resilient than previously believed. Dynamical behavior also proved difficult to reconcile. Models that accurately predict the motion of smaller bodies struggled to accommodate the refined trajectory data of 3I Attilas without adjustment. To match observations, parameters related to mass, density, and internal structure had to be altered beyond typical values. These adjustments worked mathematically, but they revealed a deeper issue. The models were being stretched to fit a reality they were never designed to handle. Another complication arose from population statistics. Existing models estimate how many objects of various sizes should exist based on known formation processes. The presence of 3I Attilas at such a scale appeared statistically improbable within these frameworks. If the models were correct, encountering such an object should be exceedingly rare. Its detection therefore suggested either extraordinary luck or an incomplete understanding of how frequently such objects are produced and preserved. This tension between observation and theory is a defining feature of scientific progress. When models fail to explain new data, they signal the need for revision rather than rejection. In the case of 3I Attilas, scientists began exploring alternative scenarios, including variations in formation environments, unusual material properties, or evolutionary paths that had not been widely considered. Each possibility required rethinking assumptions that had long been taken for granted. The struggle to explain 3I Attilas underscored a crucial lesson: models are tools, not truths. They are approximations built from available evidence, and their limits are revealed by discoveries that fall outside expectations. By challenging these models, 3I Attilas did more than raise questions about a single object. It highlighted gaps in our understanding of cosmic processes and opened the door to more comprehensive theories capable of accounting for the universe's full range of complexity. The implications of 3I Attilas went far beyond a single object, because its confirmed size forced scientists to re-examine some of the most basic assumptions about how large bodies can form and endure in space. For decades, prevailing theories have suggested natural limits to growth and longevity. These limits are not arbitrary, they arise from physics itself. As objects grow larger, the forces acting on them increase in complexity and intensity, often leading to fragmentation, instability, or destruction. The existence of 3I Attilas at such a scale challenged the idea that these limits are as strict as once believed. Traditional formation models rely heavily on gradual accumulation. Small particles collide, stick together, and slowly grow into larger bodies. However, this process becomes increasingly inefficient as size increases. Collisions grow more violent, and instead of merging, objects are more likely to shatter. According to these models, reaching an extreme size without catastrophic disruption should be exceptionally rare. Yet 3I Attilas appeared to have done exactly that, implying that either growth can occur under conditions not yet fully understood, or that alternative formation pathways exist. Survival presents an even greater challenge than formation. Space is not a gentle environment. Large objects must withstand gravitational stresses from nearby bodies, tidal forces during close encounters, and long-term exposure to radiation and thermal cycling. Over immense timescales, these forces are expected to weaken structures, erode material, and alter shape. Existing theories suggest that only smaller or exceptionally dense objects can survive unchanged for extended periods. The apparent integrity of 3I Attilas contradicted this expectation, suggesting that resilience in space may be more achievable than models predict. This forced scientists to reconsider the role of composition and internal structure. Perhaps certain materials are far stronger or more cohesive than assumed. Perhaps internal layering, porosity, or bonding mechanisms provide unexpected stability. If 3I Attilas possesses such properties, it would imply that survival is not solely a matter of size, but of internal architecture. This realization opened new avenues of research into how structure, not just mass, influences endurance in cosmic environments. Environmental factors also came under scrutiny. It is possible that 3i ATLAS formed or evolved in a region of space far calmer than those typically modeled. Lower collision rates, fewer gravitational disruptions, or unique thermal conditions could allow large objects to grow and persist. If so, it suggests that our understanding of cosmic environments is incomplete, and that certain regions may be far more conducive to preservation than previously thought. The broader implication was unavoidable: the boundaries of possibility needed adjustment. What scientists once considered unlikely or unstable now demanded serious consideration. Formation and survival models are designed to explain the majority of known objects, but rare exceptions like 3i ATLAS expose their limitations. These exceptions are not inconveniences, they are essential data points that refine theory and expand understanding. By forcing a reassessment of how large objects come into being and remain intact, 3i ATLAS acted as a catalyst for conceptual change. It reminded scientists that nature often finds ways to operate beyond simplified expectations. The universe does not adhere strictly to averages or probabilities. Sometimes, it preserves the improbable, and in doing so, it reveals that the rules governing formation and survival are broader, more flexible, and more complex than once assumed. One of the most striking revelations about 3i ATLAS was the evidence of extraordinary structural resilience it displayed against the harsh forces of space. In the cosmic environment, survival is never guaranteed, especially for large objects. Space subjects bodies to relentless stresses, gravitational tides, radiation exposure, temperature extremes, and high-velocity interactions with dust and debris. For an object of such confirmed size to remain coherent suggested a level of durability that exceeded common expectations. Gravitational forces alone pose a major threat to structural integrity. As large objects travel through regions influenced by massive bodies, they experience tidal stresses that can stretch, compress, and fracture them. Many known objects show clear signs of these effects, including fragmentation or dramatic reshaping over time. Yet 3i ATLAS exhibited no obvious indications of having been torn apart or destabilized, implying that its internal structure could absorb or redistribute these stresses more effectively than typical models predict. Thermal stress adds another layer of difficulty. Objects in space are exposed to extreme temperature variations as they move between regions of intense radiation and deep cold. Repeated heating and cooling cycles can weaken materials, create fractures, and lead to gradual disintegration. The continued stability of 3i ATLAS suggested either an exceptional resistance to thermal fatigue or a composition that minimizes expansion and contraction. This raised questions about the nature of its materials and how they might differ from those commonly observed. Radiation exposure over long periods further challenges survival. High-energy particles can alter molecular bonds, erode surfaces, and change mechanical properties. Over immense spans of time, these effects accumulate, often degrading even robust materials. The fact that 3i ATLAS appeared largely intact implied either a relatively young history or, more intriguingly, a structure capable of withstanding prolonged radiation without significant deterioration. Another factor is mechanical cohesion. Many large objects are thought to be loosely bound aggregates rather than solid monoliths. Such rubble pile structures are particularly vulnerable to disruption under stress. The behavior of 3i ATLAS, however, suggested a level of cohesion inconsistent with a loosely bound assembly. Its resilience hinted at stronger internal bonding, whether through material composition, compaction, or an internal framework that provided additional stability. These observations forced scientists to reconsider assumptions about the fragility of large objects. Structural resilience is often treated as a limiting factor, constraining how big an object can become before it inevitably breaks apart. 3i ATLAS challenged this notion by demonstrating that resilience may scale differently than expected. Size alone may not dictate vulnerability. Instead, factors such as internal structure, formation history, and environmental exposure could play decisive roles. The implications extended beyond a single object. If 3i ATLAS could endure such conditions, others might as well. This possibility suggested that the population of large, resilient bodies could be underestimated, hidden from detection by assumptions about instability. In revealing its unexpected durability, 3i ATLAS did more than surprise scientists. It expanded the conceptual space in which resilience is considered possible, encouraging a deeper exploration of how nature constructs objects capable of surviving the universe's most demanding conditions. The survival of 3i ATLAS implied that it had endured an extraordinary range of extreme conditions over a vast span of time. Space is not static, and an object traveling through it is continuously shaped by its environment. Long-term exposure to radiation, gravitational interactions, and thermal extremes typically leaves unmistakable signatures on celestial bodies. The apparent persistence of 3i ATLS suggested a history marked by repeated challenges that it somehow overcame. Radiation is one of the most pervasive forces acting on objects in space. High-energy particles originating from stars and cosmic events bombard surfaces relentlessly. Over time, this exposure alters chemical bonds, erodes material, and can weaken structural integrity. For many objects, prolonged radiation leads to surface degradation and internal changes that compromise stability. The condition of 3i ATLS implied either remarkable resistance to such damage or a capacity to absorb and dissipate energy without catastrophic effect, raising important questions about its composition and internal makeup. Gravitational forces present another major test of endurance. As an object moves through regions influenced by planets, stars, or dense clusters, it experiences varying gravitational pulls that can stretch and distort it. Close encounters can impose tidal forces strong enough to fracture or disassemble large bodies. Over long timescales, even distant interactions can gradually alter trajectories and internal stress patterns. The continued coherence of 3i ATLS suggested that it had survived multiple gravitational challenges without losing its overall structure. Thermal extremes add further stress. Objects in space often swing between intense heating and deep cold as they pass through different environments. These temperature fluctuations cause expansion and contraction that can weaken materials over time. Repeated thermal cycling is known to create fractures and accelerate decay. The fact that 3i's ATLS appeared to remain intact implied a resilience to thermal fatigue that exceeded typical expectations, pointing again toward unusual material properties or structural design. The combined effect of these forces over time is cumulative. Radiation, gravity, and thermal stress do not act in isolation, they interact, amplifying their impact. Survival under such conditions suggests not only strength, but adaptability. 3i ATLS may have internal characteristics that distribute stress evenly or prevent the propagation of fractures. Alternatively, its history may include long periods spent in relatively stable environments, punctuated by occasional extreme events it managed to withstand. This endurance carried significant implications for age. An object capable of surviving such a range of conditions could be far older than initially assumed. Longevity on this scale would mean exposure to countless cycles of cosmic change, making 3i ATLS a potential record of processes spanning immense timescales. Its very existence hinted at histories far longer and more complex than those typically considered for objects of similar classification. By implying survival through radiation, gravity, and thermal extremes, 3i ATLS forced a reevaluation of what endurance in space truly means. It suggested that the universe is capable of preserving large, coherent structures far longer than previously thought. This realization expanded the boundaries of survivability and challenged the assumption that extreme conditions inevitably lead to destruction. The discovery of 3i ATLS ultimately highlighted a fundamental limitation in how observations are often interpreted: the reliance on assumption-based frameworks. In the early stages of detection, astronomers must make reasonable assumptions to process vast amounts of data efficiently. These assumptions are not careless guesses, they are statistically grounded shortcuts that allow science to function at scale. However, the case of 3i's ATLS demonstrated how such assumptions, while useful, can also obscure extraordinary realities when they go unchallenged. One of the most common assumptions involves typical object properties. When a new body is detected, its brightness is often translated into size using standard values for reflectivity and composition. This approach works well for the majority of known objects, but it quietly embeds an expectation of normality into the analysis. In the case of 3i ATLS, this expectation shaped early conclusions, leading researchers to interpret faintness as small size rather than questioning whether the object might possess unusual surface or structural characteristics. Another assumption lies in statistical likelihood. Most detected objects fall within familiar size and behavior ranges, so ambiguous data is naturally interpreted to fit those patterns. This is a practical necessity when dealing with millions of detections, but it also creates a blind spot for rare outliers. 3i ATLS occupied this blind spot. Its early data did not strongly contradict expectations, so it was treated as routine. Only when inconsistencies accumulated did scientists begin to question the underlying assumptions guiding their interpretations. The object also exposed how early classifications can influence later analysis. Once an object is labeled as ordinary, subsequent observations are often framed within that context. Models are adjusted slightly rather than reimagined entirely. This cognitive momentum is subtle but powerful. With 3i ATLS, initial classifications delayed recognition of its true nature because new data was first forced to fit an existing narrative instead of prompting a reevaluation of the narrative itself. This realization prompted a broader reflection within the scientific process. Assumptions are essential, but they must remain flexible. The case showed the importance of designing observational pipelines that are sensitive not only to expected patterns, but also to deviations that may signal something unusual. It reinforced the value of revisiting early data with fresh perspectives once new information becomes available. 3RLS also demonstrated the danger of overconfidence in established models. When models work most of the time, it is easy to forget that they are approximations rather than absolute representations of reality. The universe does not organize itself to match human expectations or statistical averages. Rare events and exceptional objects exist precisely because nature explores possibilities beyond the most common outcomes. Assumption-based observations, if left unchecked, risk filtering out these possibilities before they are fully recognized. By revealing these limitations, 3RLS did more than refine a measurement, it served as a methodological lesson. It reminded scientists that discovery often begins where assumptions fail. True understanding requires not only better instruments and more data, but also the willingness to question the frameworks through which that data is interpreted. In doing so, the object reinforced a core principle of science. Progress depends as much on challenging expectations as it does on confirming them. The unfolding story of 3RLS strongly emphasized the essential role of patience, verification, and precision in scientific discovery. In an age where rapid results and instant conclusions are often expected, this case stood as a reminder that meaningful understanding rarely emerges from haste. Instead, it develops through careful observation, repeated testing, and a disciplined refusal to accept early impressions as final truths. Patience was required from the very beginning. The object did not reveal its significance in a single observation or dramatic moment. Its importance emerged slowly through extended tracking and the accumulation of data over time. Each new measurement added only a small piece to the overall picture, and it took sustained attention to recognize that those pieces did not fit comfortably within existing explanations. Without patience, these subtle discrepancies might have been dismissed as noise or error, and the opportunity for deeper insight would have been lost. Verification played an equally critical role. Every unexpected result demanded confirmation through independent methods. Rather than relying on a single dataset or instrument, researchers sought corroboration across multiple observation techniques. Brightness measurements were checked against spectral data. Trajectory models were refined with additional positional information, and assumptions were repeatedly tested against alternative scenarios. This process of cross-verification ensured that conclusions were not the product of chance, bias, or technical artifacts. Precision was the foundation that allowed both patience and verification to be effective. Small uncertainties can lead to large misinterpretations, especially when dealing with distant objects. In the case of 3RLS, improved precision in distance estimates, motion tracking, and reflectivity analysis gradually narrowed the range of possible explanations. Each refinement reduced ambiguity, replacing speculation with evidence. Precision transformed vague suspicion into measurable reality. The case also highlighted how these principles work together rather than in isolation. Patience without precision risks endless uncertainty, while precision without verification can create false confidence. Verification without patience may overlook long-term patterns that only emerge over time. The study of 3RLS succeeded because all three elements were present, reinforcing one another at each stage of the investigation. This approach contrasted sharply with the temptation to draw early conclusions. Initial data could have supported a comfortable, conventional interpretation, and moving on would have been easy. Instead, scientists allowed doubt to persist until it could be resolved by stronger evidence. This restraint is a defining feature of rigorous science. It acknowledges that uncertainty is not a weakness, but a signal that more work is needed. Beyond this single discovery, the emphasis on patience, verification, and precision carries broader implications. As observational capabilities improve and data volumes grow, the risk of misinterpretation increases alongside opportunity. The experience of 3RLS demonstrated that technological advancement must be matched by methodological discipline. Faster detection does not eliminate the need for careful analysis, it amplifies it. In highlighting these principles, 3RLS reaffirmed the values that underpin reliable knowledge. The object did not force new understanding through spectacle or immediacy. It did so through quiet persistence, revealing that the most transformative discoveries often depend on the slow, deliberate practices that ensure truth is distinguished from assumption. As the significance of 3RLS became clear, it began to take on a new role beyond that of a single extraordinary discovery. It evolved into a benchmark, a reference point against which future observations and theories would be measured. In science, benchmarks are crucial because they anchor understanding, providing concrete examples that define the limits of what is known and what must still be explored. The confirmed characteristics of 3I at ELAS placed it firmly in this role. Once an object reaches benchmark status, it reshapes how data is interpreted. Future detections of similar bodies are no longer evaluated in isolation. They are compared to an established standard. For researchers, 3I offered a tangible case study that embodied a set of extreme properties, size, resilience, and stability, that had previously been considered unlikely. Any new object approaching or exceeding these properties would immediately attract attention, guided by the precedent 3I at ELAS had set. This benchmark role also influenced theoretical development. Models are often tested against well-characterized examples, and 3I at ELAS provided such a test. Theories about formation, survival, and population distribution now had to account for its existence. If a model could not accommodate an object like 3I at ELAS, it was incomplete. In this way, the object became a filter through which competing explanations were evaluated, strengthening those that could explain it and exposing weaknesses in those that could not. In practical terms, 3I at ELAS affected observational strategies. Detection algorithms and survey thresholds could be refined using its properties as a guide. Knowing that such a large object could initially appear faint encouraged adjustments to search criteria, reducing the risk of similar bodies being overlooked in the future. This made 3I at ELAS not just a passive reference, but an active influence on how discovery efforts are conducted. The benchmark status also extended to education and communication within the scientific community. Well-defined examples are essential for teaching complex concepts and for aligning understanding across different research groups. 3I at ELAS offered a shared point of reference, allowing discussions about rare objects to be grounded in a concrete, well-studied case rather than abstract speculation. This common framework facilitated collaboration and accelerated progress. Perhaps most importantly, the object's role as a benchmark reshaped expectations. Benchmarks define boundaries, but they also invite those boundaries to be tested. By existing at the edge of what was thought possible, 3I at ELAS encouraged scientists to look beyond established limits. It suggested that the universe may produce more extreme examples than previously recognized, and that discovery is constrained as much by expectation as by technology. In becoming a benchmark, 3I at ELAS transcended its original identity as an anomalous detection. It became a tool for progress, a standard against which future discoveries would be weighed. Its influence extended forward in time, shaping how scientists search, analyze, and theorize, ensuring that its impact would persist long after the initial excitement of its discovery had passed. The discovery of 3I at ELAS carried an unsettling implication. If such a large and significant object could remain undetected for so long, then many others might be hidden in plain sight. This realization challenged confidence in the completeness of current surveys and suggested that the cosmic inventory may be far less complete than previously assumed. The event highlighted the possibility that detection is not only a matter of technological capability, but also of expectation and interpretation. Modern astronomical surveys are remarkably powerful, scanning vast regions of the sky with unprecedented speed and sensitivity. Yet even these systems operate within predefined parameters. Detection algorithms are tuned to recognize patterns that match known object types. When something falls outside those patterns, appearing fainter, behaving differently, or contradicting statistical norms, it may be misclassified or assigned a lower priority. 3I at ELAS demonstrated how an object can slip through this net not because it is invisible, but because it does not immediately fit expectations. This raised questions about selection bias. Surveys are designed to maximize efficiency, which often means focusing on the most common detections. Rare objects, by definition, challenge this approach. The case of 3I at ELAS suggested that rarity does not equal insignificance. On the contrary, rare objects often carry the most valuable information because they reveal the limits of current understanding. If detection systems are not optimized to flag such anomalies, entire populations may remain unrecognized. Another factor is observational perspective. An object's detectability depends on its distance, orientation, and surface properties. A large object with low reflectivity can appear deceptively small and unimportant, especially at great distances. Without sufficient follow-up, such objects may never be re-examined. 3I at ELAS highlighted how easily this can happen, emphasizing the need for sustained observation rather than one-time classification. The implications extended beyond this single case. If one object of this scale was found, statistical reasoning suggests that others may exist. They may occupy regions that are poorly surveyed, or they may share characteristics that cause them to be misinterpreted. This possibility encouraged scientists to rethink how many objects have been overlooked simply because they did not trigger immediate interest. This realization also influenced future survey design. The experience of Three Eyes ATLS underscored the importance of anomaly detection, systems that actively search for deviations rather than conformity. By training algorithms to flag unusual combinations of properties, scientists can reduce the risk of missing significant discoveries. In this way, the object indirectly improved the tools used to explore the sky. At a deeper level, the idea that many large objects remain undetected reshaped our sense of cosmic familiarity. The solar system and its surroundings are often presented as well mapped and understood, yet discoveries like Three Eyes ATLS remind us that exploration is far from complete. There are still gaps, still unknowns, and still surprises waiting to be found. By signaling the potential existence of other hidden objects, Three Eyes ATLS expanded the horizon of inquiry. It transformed a single discovery into a broader question about what else remains unseen, challenging the assumption that absence of evidence is evidence of absence, and reaffirming that the universe is richer and less predictable than our current catalogues suggest. The discovery of Three Eyes ATLS carried an unsettling implication. If such a large and consequential object could go unnoticed for so long, then many others like it may still be moving through space without recognition. This realization forced scientists to confront a difficult truth about modern astronomy, that detection is not solely limited by technology, but also by expectation. Even with powerful surveys scanning the sky every night, what is found often depends on what researchers believe they are likely to see. Modern detection systems are designed for efficiency. They are optimized to identify objects that match known patterns in brightness, motion, and behavior. This approach is necessary when processing enormous volumes of data, but it also creates blind spots. Objects that do not conform neatly to expected profiles may be classified as ordinary or dismissed as low priority. In the case of Three Eyes ATLS, its initial appearance fit comfortably within those expectations, allowing it to blend in rather than stand out. Its significance was not missed because it was invisible, but because it appeared familiar. This raised concerns about how many other objects may have been similarly overlooked. A large object with unusual surface properties or an unexpected trajectory can appear faint or unremarkable when observed briefly. Without extended follow-up, such bodies may never be re-examined in detail. The discovery of Three Eyes ATLS suggested that current catalogues may include misclassified entries, objects assumed to be small or typical that are, in reality, far more significant. The issue is compounded by observational bias. Astronomers naturally focus attention where success is most likely, prioritizing detections that promise clear results. Rare objects challenge this strategy because they require time, patience, and a willingness to investigate ambiguity. Yet it is precisely these rare objects that often yield the most transformative insights. Three Eyes ATLS demonstrated that rarity does not imply irrelevance, it often signals importance. There is also the matter of incomplete coverage. Some regions of space are observed less frequently or with lower sensitivity due to practical limitations. Objects passing through these regions may escape detailed scrutiny altogether. If Three Eyes ATLS could remain underestimated despite favorable observation conditions, it raised the possibility that similar or even larger objects could exist in less well-studied areas. This realization prompted a reassessment of detection strategies. Rather than focusing exclusively on what fits known categories, scientists began emphasizing anomaly detection, systems designed to highlight deviations from the norm. By treating unusual behavior as a feature rather than a problem, future surveys could reduce the risk of overlooking significant discoveries. Ultimately, the implication that many large objects remain undetected reshaped our sense of certainty. It reminded scientists that the absence of evidence is not evidence of absence. The cosmic neighborhood is not a closed inventory, but an evolving map with gaps yet to be filled. Three Eyes ATLS served as a quiet warning that the universe still holds far more than we have catalogued, waiting patiently for assumptions to be challenged and attention to be redirected. The confirmation of Three Eyes ATLS did more than add an extraordinary entry to astronomical records. It reshaped humanity's understanding of what is possible within our cosmic neighborhood. For many years, the space surrounding our solar system has been portrayed as largely familiar and well-charted, a region governed by predictable patterns and known limits. The discovery challenged that sense of familiarity, revealing that even nearby cosmic environments can still harbor surprises capable of redefining accepted boundaries. One of the most profound shifts lay in how scientists viewed scale. The confirmed size of Three Eyes ATLS expanded the upper limits of what was thought to exist and persist nearby. Objects of such magnitude were believed to be either exceedingly rare or unstable, unlikely to remain intact long enough to be observed. Its existence demonstrated that these assumptions were incomplete. The cosmic neighborhood is not merely populated by small, transient bodies, but can also host massive, enduring structures that defy expectations. This realization altered perceptions of risk and opportunity. Understanding what kinds of objects exist nearby is essential for accurate modeling of the solar system's dynamics. The presence of large, previously underestimated bodies affects gravitational calculations, population estimates, and long-term predictions. By reshaping these models, 3i Attilas contributed to a more realistic and nuanced picture of our surroundings, one that accounts for complexity rather than assuming uniformity. The discovery also changed how scientists approached exploration. Rather than treating the local cosmic environment as a solved problem, it reinforced the need for ongoing vigilance and curiosity. Each new observation became an opportunity to uncover something unexpected. The lesson was clear: familiarity breeds complacency, and complacency limits discovery. 3i Atlas served as a reminder that exploration does not end simply because a region has been studied before. Beyond scientific circles, the impact extended to how humanity perceives its place in the universe. Discoveries that challenge assumptions resonate because they reveal how much remains unknown. 3i Atlas underscored the idea that knowledge is provisional, always subject to revision as new evidence emerges. This humility is essential not only for science, but for our broader relationship with the cosmos. The object also reframed the narrative of progress. Advancement is often imagined as a steady march toward completeness, but discoveries like 3i Atlas show that progress is punctuated by disruptions, moments when understanding must be rebuilt rather than extended. These moments are not setbacks, they are catalysts that drive deeper insight and innovation. By reshaping humanity's understanding of what is possible nearby, 3i Atlas transformed the cosmic neighborhood from a known backdrop into an active frontier. It reminded us that even close to home, the universe retains the power to surprise, challenge, and inspire, ensuring that exploration remains a living, evolving endeavor rather than a finished chapter.